Hi everyone, another video then. This time it's a strand of differential equations. So differential equations is quite a challenging topic, I'd say, because we're nearing the end now uh, of our kind of C4 stuff. The connected rate of change is part of an overall strand of differential equations. So differential equations, what is a differential equation? Well, a differential equation is essentially, if you see dy by dx equals 3x squared, this is a differential equation because it's an equation involving the differential of a function. Do you see? So differential equations is going to come in two guises. The first is going to be when you have dy by dx equals 3x squared, right? So you're given the gradient, the differential function, and the question is, what was the original curve? So you've guessed it. I mean, hopefully you're thinking, well, the original curve is integration. So you need to integrate this thing. Do you see? Both sides. And so there's nothing new there, apart from this idea of what's called separating variables. But if you were taught that in your first year, you'd be doing that anyway. Uh, and what I mean by that is, well, how do we get y equals here? Well, what we do is we integrate the left, don't we, with respect to x. Because normally you would just go, oh, well, y equals 3x to the 3 divided by 3 plus c. But what you're actually doing is you're integrating the left and the right with respect to x. Do you see? And this is treated like a fraction, this dy by dx. Don't want to say fraction, you know, we've done substitution. You know what I mean? That dx by dx effectively cancels. Obviously it doesn't cancel, but in the maths you can treat it like a fraction, and you're left with this. The d by dx cancelled out. You're left with an integral of something with respect to y. Remember, the integral sign without a dy or a dx is meaningless. So what is it that you're actually integrating? Well, you're integrating 1, aren't you? You're integrating 1 on the left-hand side with respect to y, so that 1 just goes to y, equals now the left plus 1 to the power divided by new power plus c. Do you see? So this separating is called separation of variables, and you've been doing that all this time, you just haven't realized it. We'll get to much more complicated problems than that. But that's one strand then. So the first strand is you're going to get a huge amount of text. Let's say you have to interpret it and form a differential equation. So you've got to form it from that text, and then you need to solve it, i.e. find the general solution, so have it with the plus c in there, or find the particular solution. So really, that is an extension of your C1 stuff, right? But forming it is what people find quite hard, and we'll be doing another video on that. This video, though, is about connected rates of change. So this is the second strand of differential equations. So connected rates of change. And what this means is the chain rule, right? The chain rule. Let's, as the example says, and we're going to do a few examples of this, let's consider a box ground in size. So what do I mean by connected rates of change? Well, let's think about it. If we have a box, let's do it on here. If we have a box, because we're just chatting at the moment, aren't we? So here's a box, a cube, let's say, of length x, right? Let's say that box is expanding, it's growing. If you can imagine air being pumped into it and all of the sides maintaining their rigid structure, this thing would grow, wouldn't it? So every vertex would grow. So I'd get a bigger cube, obviously. And these vertices would match each other, wouldn't they? So this one would go to this one would go to this one would go to this, to this, You get the idea. And to this, and yet because I can't for some reason let it go, I have to complete it all. Now, what am I saying then? Well, I'm saying lots of things, aren't I? I'm saying, for example, that as x changes over time, also the volume's going to change over time, isn't it? The volume of that cube has got bigger over time. So I could make this a differential. This is the chain rule. If you see what I'm saying, let's go for it. So I'm saying that the volume. By the way, you know the chain rule. So the chain rule here, we know that dy by dx is the same as dy by dt times by dt by dx. And again, in inverted commas or quotation marks, those dt's cancel, don't they? Can we see that over time, this box is growing bigger, isn't it? dv by dx is, sorry, dv by d, yeah, so what I'm saying here is that as the volume changes, the length x changes, doesn't it? So the volume is changing as x changes. But can you see we could also put this with respect to time, couldn't we? We could write this as dv by dt. So I'm saying as the volume changes, as time changes, this could be times by dt by dx. Do you see? That is the same as that, isn't it? By the chain rule. So we're saying that as x changes, time is changing, and also as volume changes, time is changing. Do you see? But what else is changing? Well, the surface area is changing, isn't it? This surface area, so all six sides, um, are also increasing. So the area is increasing too, right? So I could say, so this is connected rates of change. It's actually it's quite simple if you understand that you're just exploiting the chain rule, and as other things change, then other things change. What's hard about it is, well, what is the question really asking me for? Can we see that as the volume changes, so this dv by dt, this could be split up, couldn't it? To be dv by dA times by dA by dt, and then we've still got our dt by dx. Do you see? Do you see how we can keep splitting up each gradient expression because they're all interconnected. They're connected rates of change. So as the volume changes, the area is changing. As the area is changing, time's changing. And as the time's changing, the side lengths are changing. Do you see? That is connected rates of change. So let's put it into a context of a question then. So at time t seconds, the surface area of a cube is A. So we're going back to the surface area, and the volume is V. The surface area of the cube, it should be of, not if, the cube is expanding at a constant rate of 2 centimeters squared per second. Find the rate at which the volume is changing. How do I approach a problem like this? I always start with, well, what's the question asking me for? Find the rate at which the volume is changing. Find the rate. The volume is changing as time is changing. So dv by dt, that's what it is we're trying to find. How do we get that? Well, we need to look at what we know. What do we know? We know that the surface area of the cube is changing at a constant rate of 2, don't we? Right? It says it right there. So maybe I can write dv by dt as a split connected rate problem. So this, what we want on the top is dv, what we want on the bottom. So notice top and bottom always diagonal to each other. And now you can think of a variable that could go in between. And what must that be? Well, it must be the dA, mustn't it? The dA and the dA must cancel. So I've got dv by dA. And what's dA by dt? Well, we know that's 2. Yeah? What is dv by dA? Well, again, if you actually drew a box like this, yeah, and called the side lengths x, so just like our example, we can think about this, can't we? What is the volume of that cube? Well, the volume must be x cubed, yeah? What is the area of that cube? Well, that must be 6x squared. So can you see that we could split this up even further, this dv by dA, because I'm not sure if you could see it, but dv by dx you can see is 3x squared, can't you? You can see that dA by dx is 12x, right? Just move that over there. 12x. And therefore, by the chain rule, dv by dA, what we want on the top, what we want on the bottom, and we've still got the 2. Can you see we can make the variable dx and they, inverted commas, cancel. So dv by dx we know is 3x squared. dx by dA, well that is dA by dx reciprocated, isn't it? So the reciprocal of that times by 2, and therefore we have 6x squared over 12x, and that gives us x over 2. There we go. Done. That is our rate at which the volume is changing. Let's go again. Example 2. The head of a snowman of radius r centimeters loses volume by evaporation at a rate proportional to its surface area. Okay, let's bear in mind what that proportion means, how we translate that into maths. Assuming that the head is spherical and that the volume of a sphere is this, and the surface area is this, write down a differential equation for the rate of change of the snowman's head. Well, this is kind of leaking into that first section of the differential equations business, because we happen to got a bit of information. We need to write down what that differential equation is. So let's start. The head of a snowman of radius r loses volume. So it's losing volume over time, and it says it's a rate proportional to its surface area. So proportional is represented by that fish sign, and as it's losing volume, it needs to be a minus. You have to be really careful with that minus. And how do we translate that? Hopefully we recognize from GCSE, we can call that minus k. So whenever we see that fish sign, or when it says proportional, for us that means we're instantly writing equals k, right? So this translates to equals k lots of. It's proportional to, it's a multiple of. So dv by dt must be minus ka, where a is the surface area. We know what we're trying to find. We're trying to find the rate of change of the radius of the snowman's head. So the radius we know is r. So we want the rate of change of the snowman's head. We need dr over dt. I know dv by dt. So by the chain rule, what we want on the top, what we want on the bottom, and now we need a common variable, and it makes sense to use dv. So we know dv by dt, we've got it here. That's minus k lots of a, so minus k a. And what is dr by dv? Well, we know that the volume is 4 over 3 pi r cubed. So if I need dr by dv, I first need to find dv by dr and then 1 over it. So the power comes down 4 pi r squared times by the 3's cancelled, so I've got 4 pi r squared. So this dr by dv is 1 over 4 pi r squared. And what is the area? The area, it was already told us, so that's this a here, is 4 pi r squared. So 4 pi r squared times by minus k, 4 pi r squared. So the answer is just minus k. Okay, so it's a constant rate. It's a constant evaporation of that head. Last one then, formal example. This is the kind of thing that you should expect to find. Very similar. So it says the volume of the sphere is increasing uniformly at a rate of 3 centimeters cubed. So it doesn't say proportional. It doesn't say proportional, so you're just instantly writing equals. So volume of a sphere, dV by dt equals 3. It wants us to find dr by dt when the radius of the sphere is 4. So dr by dt, that's what it wants. We need to use the chain rule then to get it in the variables that we have. So what we want, the variable I know is v, so dv. dv by dt, we've just said is 3. And dr by dv, again, I need to know that the volume of the sphere, it says it right there, is 4 pi r cubed over 3. dv by dr, then the power comes down, so that's 12 pi r squared over 3, so that's still going to be 4 pi r squared, but 1 over that, so 1 over 4 pi r squared, and so that's 3, 4 pi, and this is going to be at when the radius is 4, so 4 squared in there. So therefore, dr by dt is going to equal 3 divided by 4 times 16 times pi, which is 0.0149. And that's the free SF. Okay, there's our answer for part A. For part B, it says find the rate at which the surface area of the sphere is increasing when the radius is 4. So again, find the rate, the surface area. So I need find the rate of the surface area over time, don't I? So let's think about that. dA by dt, again, chain rule. This is what we want, And notice that it's still when the radius is 4. So this time our variables must be dr, mustn't it? So dr by dt, we already know, is this at 4, so 0.049, that's that. And dA by dr, it's similar to what we did here. A, we've already been told, is 4 pi r squared, so 4 pi r squared. Therefore, dA by dr is going to be, 2 comes down, 8 pi r. So there's 8 pi r, and we know that this is when r is 4. So here's our answer. So take our answer times 8 times 4 times pi, and we get 3 over 2. So 1.5 is our answer. That's it for connected rates of change. The trick is, can you recognize that it is a connected rate of change problem? We'll see.